What if reality is a quantum illusion? Everything you see feels solid, reliable, and unquestionably real. The ground beneath your feet, the device in your hands, even the sound of this voice seems to confirm one simple truth: reality is exactly what it appears to be. But what if that certainty is an illusion? What if the world you experience every moment is not the true nature of existence, but a carefully structured appearance shaped by deeper, stranger rules? Welcome to Information World. For centuries, humans believed reality was built from solid objects moving through empty space, governed by clear and predictable laws. That view felt intuitive, comfortable, and complete. Yet modern physics has been quietly dismantling this picture, revealing a universe far more mysterious than common sense ever imagined. At the smallest scales of existence, reality behaves in ways that defy logic, intuition, and even language itself. This is the realm of quantum physics, where particles can exist in multiple states at once, influence each other instantly across vast distances, and seemingly decide how to behave only when they are observed. The idea that reality might be a quantum illusion does not come from science fiction or philosophical speculation alone. It emerges from real experiments, precise mathematical models, and decades of careful observation. When physicists look deeply enough, they do not find tiny solid building blocks. Instead, they find probabilities, wave functions, and relationships that only become concrete when measured. This raises a profound question: is the reality we experience fundamental, or is it a surface-level effect created by deeper quantum processes? To understand this idea, we must first challenge one of our strongest assumptions, that objects exist with definite properties whether we look at them or not. In everyday life, this assumption works perfectly. A chair remains a chair even when no one is in the room. A mountain does not vanish when no one sees it. Classical physics, the physics of everyday objects, is built entirely on this assumption. But at the quantum level, nature refuses to behave this way. In quantum mechanics, particles such as electrons do not have a single, well-defined position or speed until they are measured. Instead, they exist in a superposition, a state that includes multiple possibilities at the same time. An electron is not here or there, it is described by a mathematical wave that represents all the places it could be. Only when a measurement is made does one of these possibilities become actual. This is not a limitation of our instruments or our knowledge. It is not that we simply do not know where the electron is. According to quantum theory, the electron truly does not have a definite position until it is observed. Reality, at this level, is not made of facts but of probabilities. One of the most famous demonstrations of this strange behavior is the double-slit experiment. When particles such as electrons are fired at a screen through two narrow slits, they create an interference pattern, a pattern of light and dark bands that is typical of waves. This happens even when the particles are sent one at a time. Each particle behaves as if it passes through both slits simultaneously and interferes with itself. But when detectors are placed to observe which slit the particle goes through, the interference pattern disappears, and the particles behave like ordinary objects. The mere act of observation changes the outcome. This is not because the measuring device physically disturbs the particle in a classical way. Even in carefully controlled experiments, where the disturbance is minimized, the effect remains. Observation itself seems to play a fundamental role in shaping reality. This leads to a deeply unsettling implication: reality is not fully defined until it is observed. The universe, at its most basic level, appears to exist in a state of potential rather than actuality. What we experience as solid, stable reality may be the result of constant interactions, measurements, and observations that collapse these potentials into definite outcomes. Another phenomenon that challenges our understanding of reality is quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. This connection appears to be instantaneous, defying the classical idea that information cannot travel faster than the speed of light. Albert Einstein famously referred to this as spooky action at a distance, because it seemed incompatible with his theory of relativity. Yet repeated experiments have confirmed entanglement beyond any reasonable doubt. The universe, it seems, is not built from separate, independent pieces. At a fundamental level, it is deeply interconnected. If particles do not have independent properties and can influence each other instantly across space, then the idea of a local, objective reality becomes difficult to maintain. Reality begins to look less like a collection of individual objects and more like a single, unified system in which relationships matter more than things. Some interpretations of quantum mechanics take this idea even further. According to the relational interpretation, properties such as position, momentum, and even existence itself are not absolute. They only exist relative to other systems. A particle does not have a definite state on its own, it has a state only in relation to something else that interacts with it. From this perspective, reality is not a fixed stage on which events unfold. It is a dynamic network of interactions. What is real for one observer may not be real in the same way for another. There is no single, observer-independent description of the universe that captures everything at once. This challenges the classical idea of an objective reality that exists entirely independent of observation. Instead, reality becomes participatory. Observers are not passive witnesses but active participants in the unfolding of the universe. The role of the observer has led some thinkers to speculate about the connection between consciousness and quantum mechanics. While this topic is often misunderstood or exaggerated, it raises important questions. Does consciousness play a special role in collapsing quantum possibilities into actual outcomes? Or is observation simply any interaction with the environment, regardless of whether a conscious mind is involved? Most physicists favor explanations that do not require consciousness to play a fundamental role. The process of decoherence, for example, explains how interactions with the environment cause quantum systems to lose their superpositions and appear classical. As particles interact with countless others, their quantum possibilities effectively collapse into stable outcomes. This creates the illusion of a classical world made of solid objects with definite properties. But even decoherence does not fully resolve the mystery. It explains how quantum behavior becomes hidden, but not why a particular outcome is chosen. The question of why we experience one specific reality rather than all possible ones remains open. Some interpretations, such as the many worlds interpretation, offer a radical answer. According to this view, all possible outcomes of quantum events actually occur, each in its own branching universe. When a quantum measurement is made, the universe splits into multiple versions, each realizing a different possibility. We experience only one branch, giving us the impression of a single, definite reality. In this framework, reality is far larger than what we perceive. What we call the universe may be just one thread in an unimaginably vast multiverse. The solidity and consistency of our world arise not because other possibilities do not exist, but because we are confined to one particular branch. Whether or not this interpretation is correct, it highlights an important point: the reality we experience may not be the full story. It may be a limited perspective shaped by the way information is processed and observed. Information itself has become a central concept in modern physics. Some physicists argue that information, not matter or energy, is the most fundamental ingredient of reality. From this viewpoint, particles are not tiny objects but carriers of information. Physical laws describe how information is transformed, transmitted, and conserved. If reality is fundamentally informational, then the physical world we perceive could be understood as an interface, a user-friendly representation of deeper informational processes. Just as a computer screen displays icons and windows that hide the complexity of electronic circuits and code, our senses may present a simplified version of reality that is optimized for survival rather than truth. This idea is supported by research in cognitive science and evolutionary psychology. Our senses did not evolve to reveal the true nature of reality. They evolved to help us survive and reproduce. Seeing reality as it truly is, at the quantum or cosmic level, would offer no advantage in everyday life. Instead, we perceive a stable, classical world that allows us to navigate, predict, and control our environment. From this perspective, reality as we experience it is not false, but incomplete. It is a useful illusion, a practical interface that hides deeper layers of complexity. The quantum world operates behind the scenes, shaping outcomes in ways that only become apparent under extreme conditions or careful experimentation. Even space and time, which feel like the most fundamental aspects of reality, may not be what they seem. In quantum gravity theories, space and time are not fundamental entities but emergent properties. They arise from more basic relationships at the quantum level. At the smallest scales, the familiar notions of distance and duration may lose their meaning entirely. If space and time emerge from deeper processes, then the idea of a fixed, objective reality located at specific points in space and moments in time becomes questionable. Reality may be more like a constantly updating pattern of relationships, with space and time acting as convenient coordinates rather than ultimate foundations. This view resonates with certain philosophical traditions that have long questioned the nature of reality. Philosophers have argued for centuries that what we perceive is not reality itself but an appearance shaped by our senses and minds. Quantum physics does not prove these philosophical ideas, but it gives them a surprising scientific echo. The notion of a quantum illusion does not mean that reality is fake or meaningless. On the contrary, it suggests that reality is far richer and more subtle than it appears. The world of everyday experience is real in the sense that it is consistent, shared, and governed by reliable rules. But it may not be fundamental. It may be a higher-level pattern arising from deeper quantum dynamics. Understanding this can profoundly change how we see ourselves and our place in the universe. If reality is not a collection of isolated objects but an interconnected web of processes, then separation is not as absolute as it seems. The boundaries between observer and observed, subject and object, become less rigid. This does not mean that individual identity disappears or that science loses its objectivity. It means that objectivity must be understood in a new way, one that accounts for the role of relationships, interactions, and perspectives. The idea that reality is a quantum illusion also invites humility. Our intuitions, shaped by everyday experience, are not reliable guides to the fundamental nature of existence. The universe is under no obligation to make sense to us. Yet through careful experimentation and mathematical reasoning, we have glimpsed a deeper layer of reality that challenges and expands our understanding. As research continues, new theories and experiments may reveal even more surprising aspects of the quantum world. We may discover that reality is stranger than any current interpretation suggests, or we may find a unifying framework that makes these mysteries feel more natural. Either way, the journey itself reshapes how we think about knowledge, truth, and existence. In the end, asking whether reality is a quantum illusion is not about denying the world we live in. It is about recognizing that what we experience may be just one layer of a much deeper structure. The solid world of objects and events may emerge from a realm of probabilities, information, and relationships that defy classical logic. Reality, then, is not a static thing but an ongoing process. It is something that happens, not something that simply is. And in that process, observation, interaction, and perspective play a central role. If this is true, then the universe is not a cold, indifferent machine running independently of us. It is a participatory system in which our interactions matter. Not because we control reality at will, but because reality itself is defined through interaction. That idea does not diminish the wonder of the universe. It deepens it. It suggests that beneath the familiar surface of everyday life lies a vast, dynamic, and mysterious foundation, one that invites curiosity rather than certainty. And perhaps the greatest illusion is not that reality is unreal, but that we have already understood it. If you enjoyed this exploration and want more deep, mind-expanding ideas like this, don't forget to like the video and subscribe to Information World for more content like this.